So our next speaker will be Andreas Lindhe. Presenting on the dynamic water balance modelling for risk assessment and decision support on MAR potential in Botswana. Thank you, Andreas.
Thank you very much. Yeah, I'm from Chalmers University of Technology in Sweden, so I work with risk assessment and decision support models on drinking water supplies. So I will present a study where we developed a risk-based model for assessing the potential effects of implementing managed aquifer recharge. And the effect we're looking at is the possibility to increase the water supply safety, which means to meet the demand over time. So I will not focus on the detail on the design of the schemes that are considered here, but rather on the effect of them. So first, some words just about the case study area. So Botswana, an arid to semi-arid climate, which means it has low rainfall, 200 to 400 millimeters per year, and at the same time have a potential evaporation of 2,500 millimeters. So it's a very water-stressed area with low levels of natural groundwater recharge, and in combination, the water demand is looking here from 2012 to 2035, and the reason is that corresponds to the planning time for the Natural Water Master Plan. So the demand is expected to increase almost double during this period, going from 72 million cubic meters per year for the entire country to 147. So, well, integrated water resource management is, of course, needed here and considered in combination with a set of other measures, including both measures to reduce water losses, water-saving technologies, and reuse and recycling of water as well. So, based on this, the water supply in the country today, groundwater is used in many parts of the country, but the main drinking water supply, and when I say the main, I mean the largest one, which includes the capital city and most of the eastern part of the country, is heavily based on surface water dams. So there is a number of surface water dams that has been built and used in combination with groundwater, and I will come back to that. But the issue is when you have these droughts and have one or several years with no rainy season at all. So the local partners, they have been considering this and seen that, well, we need to do something to secure the water supply in the future, and then managed aquifer recharge is one of those things that have been interesting to look further into. So that's the aim of the project that we was involved in. It was a pre-feasibility study, you can call it. So the aim was to enable a holistic assessment of the potential of using large-scale MAR to implement and improve the water supply safety in Botswana. And the key specific objectives was to develop this, what we call the water supply safety model, which is a dynamic water balance model, and use that to simulate and predict water shortage over time. And then to model a set of scenarios to look at both managed aquifer recharge and non-managed aquifer recharge scenarios and see how the water supply safety will develop over time. So this was a collaboration between us at Chalmers University of Technology, the local partners, which was the Department of Water Affairs and the Water Utilities Corporation. And the finance was both from the local partners and from the Swedish International Development Cooperation Agency. So I will jump into the water supply safety model. So this is a dynamic model and probabilistic, so we consider uncertainties in most of the input data into the model. And we have included all the different major components of the supply system. And the supply system I'm referring to is what they call the north-south carrier system. It's a bulk water supply system which transfers water from the northern part or the northeastern part of the country to the southeastern part of the country. It's 360 kilometers long. And the system includes 6 surface water dams, 8 well fields, 7 waterworks, and 18 demand centers. So the demand centers are the small and big cities and villages here. So the water is transferred in different directions and treated at different spots here in the system. So we built a model that could consider all these different parts of the model, the system, how the water can be transferred, the capacity, different failures that may occur, etc., etc. So we modeled the system for 23 years, and I said before it was due to the plan period that the National Water Master Plan is based on. So that's the reason for that. And we used a 1 month time step in the modeling work here. So I'll just give an overview of the main parts of input and what we consider in the model. So the main parts are the water balance calculations for the dams and the well fields. And we then compare the possible supply to the demand that we have in the different nodes in the system. And the calculations are done using Monte Carlo simulations, and we have a set of operational rules that define how the system may be operated. And we have different parameters defining capacities of different parts of the system, including also failures that may occur in the distribution system. However, one of the most important inputs to the model is that we have used a set of historical data, inflow data, to the dams, the 6 dams that we have included in the model. So based on, we had 8 years historical data. Based on that, we did an analysis of that time series and generated a set of new possible time series that we could sample from when running our model. And we used annual data and transferred it into monthly data based on historical data. So that's how we get an inflow to the dams. And then for each dam, we consider a set of parameters to see how much water can be stored. We consider the initial storage, the inflow, the evaporation, seepage, well, capacity when it comes to abstraction and other aspects. And for the same, in the same way, we consider for the well fields, for those not using managed aquifer recharge, we only consider the sustainable yield for those. But for the managed aquifer recharge well fields, we looked at, well, the storage when we started simulation, the natural groundwater recharge, inflows and outflows, abstraction rates and injection rates. So the idea in this case is to use aquifer storage and recovery system, so using injection wells. And then when we can calculate the possible supply, we compare, as I said, with the actual demand, and we get a set of different results, but some of the key ones are that we can calculate the probability of having a shortage and the magnitude of the shortage. And we can do that for each time step in the model and for each demand center. So that's the main parts and main steps in the modeling. And jumping to the scenarios that we have looked at. So we have modeled a set of scenarios. I will focus on the 3 most important ones, which was the current system in 2013 when we started the project. The current system with an additional dam that has now been built and is in operation. And finally then looking at when implementing managed aquifer recharge at two major areas that is considered for this. So looking at the initial situation then, well, you see here on the right side, the graph here illustrates the expected annual water shortage for Great Gaborone. So it's the Cadel with the connected demand centers to that, and the situation is the same for all the demand centers included, but I will focus on this part of the system. So you see increasing from almost 0 in the beginning of the model period to about 50% of the annual demand that is missing in the end of the model period. And 70% of the months included in this time period is we expect to have water shortage, and on average it's around 48% that is missing of the actual needed water. So looking then, we can look at, this is also for the initial situation, but here displayed for different magnitude shortage. So going from 2, 5, 10, 20, and 30 million cubic meters. And this is the annual the annual demand in this area is 80, so 30 corresponds to 40% of the annual demand. So seeing how the probability of different magnitudes of shortage increase over the model period here. So that's the original system. Then implementing this additional dam, you can see how the graphs, it's pushed down, so it's improved the situation heavily. However, you can see that after around 10 years, you still get a problem. And then looking at what happens when we implement the managed aquifer recharge well fields, you see that we can further improve the system. However, the effect is still a bit limited due to different factors in the system. And jumping to this graph here, what you see is, you see the red bars here illustrate the percentage of the time when injection is needed. And here we're represented with uncertainties, but looking at the mean value, in 41% of the months, we need to inject water to fill up the aquifer. However, in 34% of those times, we're able to meet the needed injection. However, the rest of the time, we are not able due to different limitations, and that's due to the dam storage, how it's operated, etc., and some other aspects such as water works capacity and so on. So if we exclude those limitations, we say that we make some measures in the system, we increase some of the capacities, etc. We can further improve the system, and that is what is shown here in the lower right graph. And there is possibility to further improve and optimize the system when it comes to when you start to pump water from the well fields and so on. So there is potential for further improvement here. So the same results can be displayed like this. This is the probability of the different magnitudes of shortage at the last year in the model period. And you see how the situation improves going from left to right, and to the far right you have this scenario when you have excluded some of the limitations. So the conclusions, well, the model itself, it provides decision support in different ways. You can model managed aquifer recharge scenarios and non-managed aquifer recharge scenarios, compare them and see what is limiting the effect, and you can also see how much it improves the water supply safety. Not only looking at how much water we can store and extract from the well fields, but how it actually affects the water supply safety. And the future work is actually the Botswana has received a loan from the World Bank now and is about to start an additional study for one of the well fields to further investigate. And our suggestion has since before been to update our model with more detailed information about the actual function of the well fields and how they may operate when implementing managed aquifer recharge. Okay, thank you.
Thank you very much, Andreas. Do we have time for one or two questions? Yes, up midway on the left-hand side, my left. Put your hand up again, please. Thank you.
Thank you. Thank you for the nice presentation. I'm wondering how you are addressing the water quality issues, because during droughts they have problems with using pit latrines, and so it contaminates the well field. And during the floods, there's a lot of contamination floating around as well. So somehow the actual available water quantity has to somehow be reduced due to those factors. Do you account for that?
Yeah, so, well, what we have considered here is we have looked at that there must be capacity for treating the water, the surface water that is injected, of course, but then what has been considered is only that the water abstracted from the well fields will also be possibly need to have some treatment. So that has been included, but we have not in detail been able to investigate and look at to what extent it may be a problem. But we have included that there must be capacity for treating the water.
Thank you, Andreas, for a very nice presentation. Obviously, the high potential evaporation rate is a big factor.
Yep.
and combined with this surface water storage. Going from surface water storage to MAR, do you have an idea of how the quantity of water that is lost by evaporation changes?
Yeah, so our idea was that we would be able to actually save quite much water just by hiding it from the evaporation. However, since we run the model based on how they currently operate the system, and due to the limitations that I showed, we were not able to actually achieve such a high amount of saving that we thought from the beginning. However, we think that by optimizing the model, the system further, we can do that. However, I don't have the figures right now, but I can give them to you.
Okay, please. Yeah.
Okay, thank you, Andreas, for this third very good presentation on this session on MAR and IWRM. Excellent, thank you very much.